Let's start this lesson by asking the question, what really happens when you hit a ball with a bat? I mean, that microsecond of time when the two collide with each other. Well, you know for sure that the ball experiences a force that is large enough to slow it down to a stop and then maybe reverse its motion. And during this time, the force F on the ball varies during the collision. And why does it vary? Simply because it is 0 right before it touches the bat and then increases to a max when the ball and bat are in complete contact and then starts reducing as the ball moves away from the bat, changing the linear momentum P of the ball. That is, this force changes the linear momentum of the ball, and this change of momentum and force are related by Newton's second law, written in the form F is equal to dP upon dt. Now, if you rearrange this equation, we find that in time interval dt, the ball's momentum changes as a product of force during time dt and dt. Now, since this change in momentum is just for the time period dt, we can calculate the total change in the ball's momentum if we integrate both sides. So let us say the collision happened between time t initial and t final, that is ti and tf. Then integrating from t initial to t final, we get on the left hand side change in momentum pf minus p initial, or let's call it delta p, and the right side, which takes into account both the magnitude and the duration of the force, is called the impulse j of the collision. So j is equal to integral f dt as time changes from t initial to t final. So we can say that the change in an object's momentum is equal to the impulse experienced by the object, and often this equation is referred to as the linear momentum impulse theorem. And it tells us two things. One is that impulse is a vector, since change in momentum is a vector. And two, the direction of impulse is always in the direction of change in momentum. Okay, now let us take this to the next level. So if we have a graph of force versus time, we can find j, or the impulse, by finding the area between the curve and the time axis, simply because j is nothing but the summation of area under an f versus time graph. Now, in many situations, we may not really know how the force changes with time, but do often know the average magnitude of the force and the time interval delta t of the collision. Then we can write the magnitude of the impulse as j is equal to f average times delta t. So you see, the area under this curve is equal to the area under the curve for the actual force, because both areas give the same magnitude of impulse j. Well, instead of finding the impulse on the ball, we could have taken the bat as a focus of study and try to find the impulse on that. So Newton's third law tells us that the force on the bat has the same magnitude but a direction opposite that of the force on the ball. Then this equation shows us that the impulse on the bat has the same magnitude but the direction would be opposite the impulse on the ball. Because you see, if you retain the magnitude but change the sign, j now has a negative sign that is opposite to what the ball experienced. Now let us say there is another force versus time curve which looks like this, and it is told that the area under this curve is the same as the area under this curve. Then we can safely say that the impulse delivered by this force for this time interval is the same as impulse delivered by some other smaller force but for a longer time interval. So you see, if any given force time combination generates the same area under a curve, the impulse delivered is the same. So if you're enjoying this video that obviously took a lot of work to put together, hit the like button. It really helps the channel. And with that being said, let's move on. So let us work around an example that will bring a lot of clarity to the topic. And what we have here is a ball of mass 0.4 kilogram thrown against a brick wall. It moves horizontally at 30 meters per second and rebounds horizontally at 20 meters per second. And we are asked to find the impulse on the ball when it collides with the wall. Also, what is asked is that if the force on the ball during the collision is constant and lasts 0.01 seconds, what is that average horizontal force that the wall exerts on the ball during the impact? So here we will take this as the positive x direction. So this becomes negative. Then we can say that the initial momentum of the ball is Pi is equal to mv1, which equals 0.4 into minus 30 meters per second, which equals minus 12 kilogram meters per second. And the final momentum is P2 is equal to mv2, that equals 0.4 into plus 20 meters per second, which equals plus 8 kilogram meters per second. Now we know that impulse on the ball is nothing but the change in its momentum. So impulse on the ball, let's call it J ball, is equal to P2 minus P1, which equals 8 minus 12, which equals 20 kilogram meters per second. To find the average force, we can make use of this equation, which says that the impulse J equals the average force multiplied by the collision time, that is T2 minus T1 is equal to delta T is equal to 0.01 seconds, or F average is equal to J upon delta T, which equals 20 divided by 0.01 seconds, which equals 2000 newtons. What you can observe here is that the sign of the impulse turned out to be positive, that is to the right, and that is what you would have actually expected, because impulse can be thought of as a kind of kick that the wall gives to the ball, and this kick quite clearly has to be to the right. Now students often find the comparison of momentum and kinetic energy a little confusing. So let us see how we should view the two quantities that are closely related to Newton's second law of motion. So the impulse momentum theorem says that a change in particles' momentum is due to impulse, which depends on the time over which the net force acts. But when we deal with the work energy theorem, we see that the kinetic energy changes when work is done on a particle, and we know that the total work done depends on the distance over which the net force acts and has no dependence on time it took. So let us say you are given the choice between catching a 0.1 kilogram ball moving at 20 meters per second or a 0.5 kilogram ball moving at 4 meters per second. Which do you think would be easier for you to catch? See, both balls have the same momentum, P of 2 kilograms meters per second. So you might be tempted to say that the effort required is the same. But you see, they have different values of kinetic energy. The large ball that is moving slower has kinetic energy of 4 joules, while the small ball moving faster has a kinetic energy of 20 joules. So let us analyze. We can safely say that since the momentum is same for both balls, both require the same impulse to be brought to rest, because change in momentum is what impulse is, and the change is the same in both cases at 2 kilogram meters per second. But you see, stopping the 0.1 kilogram ball with your hand requires 5 times more work than stopping the 0.5 kilogram ball, because a smaller ball has 5 times more kinetic energy. Let me explain this to you. So let us say you use force F with your hand to bring the ball to a stop. Then if the momentum has to be reduced to 0 from 2 kilogram meters per second, the time taken would be the same if we see this formula. That is, J is same, F is same, and so the time has to be same. And let us call it duration of the catch. But your hand will have to be pushed back 5 times more if you choose to catch this small ball that is moving faster. Because if you see this formula, displacement here is 20 joules by force F. And here it is 4 joules divided by the same force F. So if you want to minimize strain on your arms, you would like to choose the 0.5 kilogram ball to catch that has lower kinetic energy. So if you really want to understand the concept of center of mass, linear momentum and collision, I would suggest you head over to this playlist that covers all this really well. And if you like this lesson, do give a thumbs up, and I will see you in the next lesson.